Hello, everyone. My name is Jean, and I would like to welcome everyone to the last session of our spring program for the Virtual Inter-University Symposium on infrastructure and infrastructure management. And today we have two speakers, Adrian Hernandez and Francisco Contreras, and they will be presenting their work. And each of the presentation should be about, hello. Each of the presentations should be about 20 minutes long, and after which we will take questions from the audience, and we can like speak their question or send them in the chat. And I would like to point out this meeting is being recorded and will be made available shortly after. And thank you all for attending. And let me introduce our first speaker today, Adrian Hernandez. And he's the current PhD candidate in Northwestern University Transportation Program in the Department of Civil and Environmental Engineering. And at Northwestern, he's advised by Professor Pablo Durango-Cohen and has been conducting research on decarbonizing of freight rail in US. Adrian received his BS in civil engineering from Cornell University, where he researched algorithm for vehicle routing problems. Adrian has been recipients of the LSAMP Fellowship and is the current GEM Fellowship. His academic interest lies in optimization, operation research, infrastructure management, and transportation. So now let me hand over to him and
thank you, Jing. And thank you everyone again, as Jing mentioned, for joining us. So I just want to make sure, can everybody see my screen? Yes. Yeah, okay, good. Thank you. So as Jing mentioned, over the last year, I've been working on and researching the decarbonization of freight rail. So today I'll be presenting our work on, more specifically, the modeling work and some of the results that we've had from this research on locating and sizing refueling facilities on networks to support freight rail decarbonization. And so this work has been done in collaboration with researchers at Northwestern University Transportation Center, Max Ng, who's on the call, and my advisor, Professor Pablo Durango-Cohen, and PI Hanima Masani. We also have collaborators at Argonne National Lab, and it's a project that has been funded by the DOE ARPA-E. So I'd like to start off by outlining the research problem and providing some motivation for the work that we are looking at. So as a background, freight rail operations in the US are nearly exclusively powered by diesel, which is different from the case in some other countries where track is electrified. And really, the railroads here are privately owned, and they don't see track electrification as a practical solution to decarbonize freight rail. So our work was looking at alternative fuel technologies that can be loaded on current locomotives or new technology locomotives and move much like diesel fuel. So diesel locomotives have a range of over 1,000 miles and can refuel within 30 minutes. So this gives us an idea of what the incumbent technology is like that we basically need to provide alternatives for. And so the challenges for this are that providing alternative fuel technologies will require the deployment of new refueling infrastructure. Moreover, battery electric and hydrogen locomotives, which are some of the more promising technologies, have ranges that are considerably lower than diesel's range right now. New refueling facilities must also be sized to meet energy demands, which are uncertain and may change over time. So this is another complication. And facility deployment over network is complex overall due to route interconnectivity. And so there are many moving parts here that need to be accounted for if we want to optimize the deployment of infrastructure. So the overall goal is to develop a framework to address the deployment of support infrastructure for rail decarbonization. And our focus is going to be on infrastructure deployment. So namely looking at the location of charging or refueling facilities on the rail network, sizing facilities to provide adequate power or fuel, and evaluating these deployment scenarios through economic, environmental, and operational lenses. So I'd like to present what we have developed in this work, and we call it the New Friend Framework, which stands for the Northwestern University Freight Rail Infrastructure and Energy Network Decarbonization Framework. So the credit for that name goes to Professor Mamusani, who's a genius with acronyms, among other things. And so the New Friend Framework really is a comprehensive industry-oriented platform that helps users build and assess scenarios related to the deployment of advanced fuel propulsion technologies across the rail network in the US. And this was the key task item that was requested by the sponsor, the Department of Energy, in the goal. So really like a deliverable that was user-friendly and industry-oriented was what we were tasked with creating. In the remainder of the talk, I want to focus on the methodological contributions and insights that we were able to extract from the creation of this platform. So for given technologies, characteristic, and design variables, the platform yields optimal network design in the form of location of required service facilities and energy sourcing strategies. It also provides estimates of capital investments, carbon emissions, and operational impacts of a given scenario. And the power of our approach relies on extensions of nominal graph theory problems. And so these are the energy technologies that we're considering. For the remainder of the talk, I'll be focusing mainly on battery electric locomotives. So this is an overview of the 5-step New Friend Framework that I'll go into more detail in the following slides. But to give an overview, we begin by selecting OD pairs to enable and serve with the alternative technology on the network. And we do this by ranking them and selecting a subset of OD pairs based off their flow. The flow data that we have is actually estimates from the carload Weibull sample that is collected by the Surface Transportation Board in the United States on all the major railroads. So once these, the subset of OD pairs that are going to be enabled is selected, we provide these to the facility deployment or facility location model, which determines the optimal location of facilities in order to enable alternative fuel technology service along these OD pair paths. And recent work has actually worked to incorporate both of these steps into one step, and I'll touch on that at the end of the presentation. After that, we route flows on the resulting network and basically assign potential flows to the alternative technology on the resulting network. These flows are the critical inputs for the facility sizing model, which determines the optimal energy sourcing strategy to minimize costs, subject to enabling the service of the alternative technology on the network. So it requires these flows to compute energy requirement. And finally, we apply lifecycle analysis and techno-economic analysis tools developed by Argonne National Lab to estimate the economic and environmental impacts of a deployment scenario on railroads and the environment. So to start off with an example and basically walk through the methodology that we've developed, here we have the baseline network with flows routed to their shortest paths. And so the flows that are routed here are from that carload Weibull sample compiled by the Surface Transportation Board. And we consider here 277 candidate facility locations, which are potential refueling or charging, in this case, locations on the network. In other words, there's some sort of rail yard. They're currently some sort of rail yard. And the line width shows the gradient of daily ton flows on the network. So this can be used to determine OD pair and path selection. So to do that, in this case, we've selected the top 40% of OD pairs in terms of ton miles. So basically, that results in 24 OD pairs on the network, which are shown here in diamonds, with the flows on their shortest paths between them shown in the red lines. And so these represent very significant corridors on the network. For example, the northern and southern transcontinental corridors on this for this railroad. So these 24 OD pairs and their paths between them are the critical inputs to the facility location model, which seeks to minimize the costs, in this case, just the number of facilities selected. And so in this formulation, the objective shown here, we've just set the beta coefficients to 1, which is equivalent to minimizing the number of facilities. And the OD pair and their corresponding paths that we've predetermined are what we use to define these cover constraints, along with a given locomotive range R. So those two components allow us to define these cover constraints, which basically say for a given facility, we need to ensure that there is one facility along each path that we want to cover within range of it, and that there is another facility along the path preceding it so that we can reach that facility within range, right? And so that's what each of these constraints is looking, one direction forward, one direction backward along a given path. And so the results for this example considered here show that for a 600-mile range and the OD paths that were pre-specified in the prior step, we need 18 out of the 277 candidate facilities to be selected, and more specifically, these 18 shown here in the bubbles. Now, the resulting network that we get when we can connect these facilities and those within reach show that 185 nodes, or just rail yards in general, are covered by the battery network. So this actually provides an extensive coverage with a relatively optimistic range of 600 miles, but not overly optimistic. So following this, we route flows on the resulting network. And here we assume that flows can actually be rerouted from their shortest path to the longest path, so long as the distance increase does not exceed 50% the original distance. So the reason we are interested in this is to see how much can we actually capture with the alternative technology, and can we maximize basically the emissions reductions scenario with even like a relatively small range like 600 miles. And this actually results in 70% of ton miles being served by battery, which is a significant increase from the 40% design parameter that was used to specify the OD pairs that were selected. So these link flows in terms of tons are critical inputs for the energy sourcing step. So here we augment the network with a source node S, which represents, in this case, the electricity supplier for the network. And we connect this source node with each of the selected facilities with an arc. And the arc has a cost here given by P sub SI, which corresponds to the electricity rate or cost, the unit cost for that location I. So here we allow for different locations to have different costs, which is where the optimization comes in. We basically want to select the energy sourcing strategy that minimizes total cost, since there's differences in cost of electricity consumption across states in the US. And so to ensure also like energy balance and proper supply, we impose these constraints and basically just model this exactly as a form of the minimum cost network flow problem. So these are the results for the energy sourcing and the resulting facility sizing steps. So here we show the bubbles are proportional to the log of the energy required, but the more clear output is given by these numbers on it. So these numbers are provided by Argonne National Labs, their tool that uses basically the results from the energy sourcing, which is in terms of megawatt hours per day, to determine the number of chargers needed at each facility. And so here we assume chargers have power of 3 megawatts. And in this case, emissions are reduced by 43% relative to current operations, even though the percentage of total ton miles served by battery is 70%. And so this is because the current electrical grid in the US is not 100% clean, basically in any state. So this is what basically the current grid could offer. We can also look at competing objectives for the energy sourcing step, in which instead of minimizing charging costs, we can look at minimizing charging emissions, subject to these differences in emissions across states. And so we see that if we look at this objective, we're able to reduce emissions by a further 23% relative to the cost case. And this is mainly possible by shifting these like energy sourcing from dirtier states to cleaner states like California in this case. And so this illustrates some of these interesting trade-offs that our modeling platform can accommodate. So as I mentioned, there's some ongoing work at looking at different formulations for the facility location problem, particularly in updating the constraints to capture cyclic asset repositioning. And so here at the bottom, I just have the original formulation that I showed just for reference. But we've updated the formulation to capture cyclic asset repositioning. And that basically just means that we're looking at what we're trying to model operations to match freight rail more closely. And so freight rail operations will typically cycle locomotives on routes or combination of routes. And so we're trying to include these kinds of cycles instead of just looking at paths between OD pairs. We've also formulated a maximum flow capture variant where the objective has been changed to basically maximizing the flow that is captured. And we've imposed a budget constraint on the number of facilities that have been that can be selected. And this requires us to endogenize OD path selection, which is what I mentioned in the earlier stage, which adds to complexity, but also improves the optimization results of the model. Following this, we've considered a set of potential deviation paths for each OD pair. And this allows also for greater flexibility, but does bring in more complexity. So these scenarios are being resolved through the reformulations for evaluation and comparison. So this is some future work direction. And so as a conclusion, we've developed a framework to address the deployment of support infrastructure for rail decarbonization. We have created an underlying foundation based on nominal problems in graph theory. And our framework offers significant modeling flexibility in terms of scenario specification. And I'll touch on that in just a moment. And serves as a simulation and evaluation tool for infrastructure deployment. And so I just want to finish with, I guess, a reference to the new friend dashboard, which is a tool that we've created as part of the project. It's publicly available at this link here, and basically allows users to model fuel technology deployment scenarios for different fuel technologies, several railroad networks, and commodity groups. So if you're interested, please go ahead and give it a try. And so with that, I want to thank you and open for questions.
Thank you, Adrian. So is there any questions from the audience?
Oh, hi, Adrian. This is Arnold.
Hi.
Yeah, I'm not feeling extremely well. Still, the pollen allergy makes me sometimes sneezing. But yes, thank you for the great presentation. I particularly like the new friend name. It's a really great catch. Just two small, one comment and one question. A comment is for the competing objectives that you mentioned, that one with basically you had you separate this into single objective optimization, and then you get this result. Yes, that's the one.
Yes.
My question here is that is there any plan, or do you have any thought how we can guide the decision makers to make a decision between those two weights, so that we can settle down on some particular unique number between those competing objectives?
Yeah, definitely. So that's a very good question. And actually we have discussed some insights along that line. So there's basically a metric that's known as cost of avoided emissions. And I'm not sure. So I wasn't familiar with this until our colleagues at Argonne National Lab basically told me what it was. But I was familiar with the concept of the social cost of carbon, which has become more like popularized now. And it's also used to basically inform carbon taxing or incentive schemes. So if we actually, we can also, instead of setting the coefficients to be the emissions or to be the cost, we can set the coefficients to be basically the cost of avoided emissions per state. And so what does that mean in this case? That would be like the cost, the incremental cost of removing certain amount of emissions relative to some baseline in California compared to that cost in, let's say, Texas, which may be different. And so it captures the efficiency of emissions reductions of different states. And so this is kind of a way to reconcile the costs and emissions in one metric, and does yield results that often lie between these two extremes. So I know I don't have like the actual example here, but this is a direction that we could take. Yeah. Thank you.
All right. Yeah, no, that makes sense. So basically you would like to, instead of probably finalizing a single kind of a weighting vectors between these two objectives, you would rather like to leave the market to determine the weights through the carbon taxation or some other mechanisms.
Yeah, that's definitely like I think that could be one direction. Yeah, the other direction is exactly what you mentioned. It's providing some weights. What should we weigh as more important? And I think that's also that would also be like, I mean, not only implementable but interesting as well.
No, I don't know which one is better. I thought that the market system probably is more valid. I don't know. I have no idea at all. Just a comment. Yeah. Just a small question. In your earlier presentation, you mentioned something about the gradient of the daily flow. What exactly is that? Sorry for this. This should be a very small question.
No, sorry.
The gradient of a daily flow. When you say they said the line width representing something, I didn't quite catch that part.
Yeah. So I think is it here?
Yeah, somewhere. Yeah, it's whenever you had some. Yeah.
I see. Yes. Yeah, I think it should have been just basically like the volume, I think is what the proper word should be. Sorry about that.
Oh, so okay.
The line with here shows the volume, like the amount of flow in terms of points on the network.
Okay, I thought this is more kind of importance measure or sensitivity. It's not, right?
No, it's not. It's just volume on the network.
Oh, okay. All right.
Yeah.
Thank you. Yeah.
No, thank you.
Oh, I saw Christina raise hands.
Hi, Adrian. Thank you so much for your presentation. Sorry, my camera is not working well today. I have a question about your thoughts. Your framework is basically looking at the location of like charging facilities, but these technologies about like efficiencies of potentially batteries or even the efficiencies of different sustainable technologies will probably evolve over time. And so I'm wondering, how have you considered that in your study? How by the time these potential new locations are built, maybe the technologies have changed. So how have you considered that in your study?
Yeah, absolutely. That's well, first of all, thank you for attending, for joining and for your question. That's definitely a key question that we initially wanted to consider in this scope, but we saw that, you know, even just considering like a snapshot in the future is complicated enough. So we decided to start off with that and say, if we had all this information, what would optimizing some sort of like future scenario, assuming that certain parameters are fixed, be like? So this is our approach to that. Right now, we're actually following up on and taking the approach that you just mentioned in looking at what the optimal rollout of the technologies and facility locations and infrastructure would be over time. And this will take into account, or should take into account to some degree, variations in technology over time. So as you mentioned, I mean, battery technology has been evolving extremely rapidly over the last 10 years. And, you know, there's no indication that we should think that it should stop. Hopefully it continues to improve. And so that definitely should inform, should inform the model in terms of determining rollout. It would be a different problem. And so we're looking at some relevant literature that could help inform that.
Awesome. Thank you. Thank you also for providing such a complete explanation of your research. Thank you.
Thank you.
I have one question, if I may. Do you know if any countries have implemented this system of using batteries for railroads?
Yeah, so yeah, I didn't provide too much of a background in terms of what is going on, but I'm glad you bring it up. So the US, actually, several railroads in the US have run pilot studies on revenue service. So it's not even, you know, they actually are moving goods with battery technologies. A lot of them, though, are in what they call like a hybrid operation. So they run 2 diesel locomotives and 1 battery locomotive on the same train. Australia, there's some railroads in Australia that have used battery locomotives or have just started using battery locomotives for kind of like these like fixed cycle operations within mines, coal mines. So it's very ironic. But so that's those are some examples. Hydrogen is also being tested on several railroads in Canada and the US. So there is a lot of interest in these technologies. It's just about, whether they will be taken up or not. Yeah.
Thank you.
Hey, so thank you, Adrian, for the wonderful presentation, and thank you all for bringing up questions. And now I will introduce our next speaker, Francisco Contreras. He's a second-year PhD student at University of Colorado Boulder, advised by Professor Cristina Torres-Machi. Francisco obtained a bachelor degree in civil engineering at the Technology University Federico Santa Maria, Chile. His research focuses on transportation asset management and is currently working on how to measure resilience of different communities' transportation networks to flood events. So I'll hand over to Francisco and welcome.
Hi, thank you. Let me share. Hi, yeah. So this is Francisco Contreras from the University of Colorado Boulder, and today I'm going to be presenting about measuring the impact of flooding on traffic using crowdsourced data. So let's first talk about flooding. Why are we researching this? Flooding is a very common disaster in many states in the US. For example, if we look at the left figure, we see that in Texas or Louisiana, it has costed more than $5 billion in the last 8 years. And it's not only about money, it's also about lives. If we look at the right figure, we see that in 2017, there were 70 fatalities only in Texas due to flooding, and there were 179 fatalities in the whole US. So we see that flooding happens very often in the US in some states, and it is expected to be even more frequent because of more urbanization, because of climate change. So it's a common disaster, and it's expected to remain as that. And about transportation networks, flooding does also impact transportation network. For example, if we are traveling from point A to point B, and there is flooding, any degree of flooding, we could expect to have lower travel speeds. And if we have lower travel speeds, we might expect to have higher travel times. Sometimes when there is water on the roads, we might decide to take other routes because of congestion or because that road is not accessible. So we might even expect higher travel distances. And sometimes when there's a big storm out there, we might even decide not to travel, either because it will take too long or because it's unsafe. So there are different impacts of flooding in traffic. We know there are impacts, but now the question is, how do we measure these impacts? The most common way right now is through data simulation. What some researchers do is they simulate a network and they simulate some scenarios. For example, for flooding, they could say that some roads have reduced travel speed or some roads are closed. And then they run the simulation and they get the data. On the other side, we can also use real data. And traditionally, a few things that have been done is manual traffic count, in which a person just counts the traffic on for a given road. We have pneumatic tubes, which count the number of cars that are traveling. On some roads, we have sensors which measure traffic or speed. And we have also more ways to measure data. However, most of these measures are applicable only for a few roads, and we cannot put sensors in every road. So luckily, starting from 2017 to today, we have a new kind of data, which is crowdsourced traffic data. This data is obtained thanks to smartphones. So nowadays, most of us use a lot of apps that is location. These apps are registering our position throughout the day So they know where we are at different times of the day, and then so they can calculate our trips, where they are starting, where they are finishing, what's our travel speed, what distance are we traveling, and how are we traveling. So some platforms such as Streetlight Data are gathering all of this data from our devices, and they are processing it into actual traffic data. So nowadays, we can just download after paying traffic data from these platforms. And we can do this for almost everywhere in the US, for almost every road in the US, or any zone in the US and Canada. So now that we have new data sources, we have new opportunities. Now we can measure how traffic is changing during disruptive events such as flooding, which is what we are interested in. And actually, there has been one study that did something related to this. So in 2021, Prof and colleagues, they analyzed how traffic was changing due to flooding in Norfolk, Virginia. And they identified the roads that had the highest decrease in traffic. And here in this picture, we can see those roads in orange. So that's one application with this new data and flooding. However, we have a different goal in mind. We would like to be able to measure the resilience of different communities' traffic to flood events, and then explore what variables are affecting that resilience. It could be social vulnerability, could be income. We don't know yet. So this is our main goal. However, to be able to achieve this goal, we're gonna have to start with the basics, which is how do we measure resilience? So we were doing some literature review, and we found out that the most common way to measure resilience is through using resilience metrics. And this resilience metric, what they do is they measure the functionality of a system during a disruptive event. By functionality, I mean to evaluate one variable that serves as a measure of a system. For example, if we're looking at the road, we could look at traffic. How many cars do we have on a given road? And then during a disruptive event, in this case would be a flood, we would measure how much traffic we are losing during the event. So we could measure different resilience metrics. For example, one would be the total loss of functionality during the event. Another one could be the lowest functionality during the event, or the average functionality during any event. So we know how to measure resilience. We know that we need to use something as a functionality. We know we need to use functionality. However, there are a few things that are not very clear. For example, how do I know when the effects of flooding on traffic start and when they are finishing? Or how do I know which variable should I use? I mentioned that we have reduced travel speed, trips are getting longer. So we could use any of those variables. Also, how do I get this curve? Because travel speed is given in miles, but travel speed is miles per hour, but I need to get to what is the usual travel speed. So here we have different challenges that we need to address to be able to measure resilience. So these are the three challenges that I just mentioned. How do I get the start and the finish of the event? How do I get the functionality curves? And what traffic variables should I be using? So that's why we are doing this exploratory research, where we want to answer these three challenges. So we have three objectives. First, present a methodology to determine when the effects of flooding on traffic start and when they finish. Second, we want to define the process to obtain functionality curves from the crowdsourced traffic data, which in this case is Streetlight. And then finally determine the best variables to measure traffic disruption during a flood event. As I mentioned, we have lots of variables we use, which in this case are 4. We are going to see that there are 6. And we want to see which one could be used, which one don't. We could work with all of them, but that would not be a really good use of resources and time. So that's why we want to see which one are the best. So to achieve these objectives, we're going to follow the following methodology. First, we mentioned our main goal was to analyze communities. So we will be working with 3 census tracts, which are located in Texas. We chose Texas because it gets plotted very often, so we have data to work with, and we will be analyzing 3 extreme events, which in this case are Tropical Storm Imelda, Hurricane Harvey, and Hurricane Sally. In total, we are going to analyze 5 flood events. We have 3 census tracts, 3 extreme events, but we're going to have 5 events because not all census tracts were affected by the 3 storms because they are located in different places in Texas. So to achieve our 3 objectives, we're going to follow 5 steps. First, we're going to talk about the data collection, what traffic variables we got, and we're going to see we got other variables. Second, we're going to talk about traffic data normalization. We're going to see that the raw data, we cannot use it. We're going to see why. Step 3, we're going to show the methodology we're going to use to define the start at the end of the event. Step number 4, we're going to see how we got the functionality curves after step 2 and 3 are done. And finally, step number 5, we're going to see how we're going to obtain what are the best variables to measure disruption during a flood event. So let's go with step number 1. So as I mentioned, we're going to be using crowdsourced data from Streetlight, and we are going to be using census tracts. In this figure, we see one census tract that we are using, which is located near Galveston in Texas. And from Streetlight, we're going to be getting 4 traffic variables directly, which the first one is going to be the number of trips, which is in a given day, how many trips started in this census tract. Then we have the average travel length, which is going to be miles. The average travel time is going to be in minutes, and average travel speed, which is miles per hour. So these 4 variables are given directly by Streetlight, and then we calculated 2 more variables because these 2 variables are used very commonly in the literature. The first one is going to be vehicle miles traveled, or VMT, which is just a cumulative value of how many miles were traveled in all trips. Then we have vehicle hours traveled, or VHT, which is a cumulative variable of the total time traveled on all of the trips. So we're going to be analyzing these 6 variables. Also, we're going to download precipitation records from NOAA. We got the daily precipitation record for the closest station to each census tract because we're going to use that to define the start of the event. So after we downloaded all of our data for all of our events, we want to see what our traffic data looks like and why we need normalization. So here on the upper figure, we have the traffic variable of the number of clicks for one census tract for the year of 2019. And we can see a few things here. First, we can see that there is a lot of oscillation on the data. And if we look at those 2 red dots, we see that they are separated by 7 days. And actually, if we count the peaks in this year, there are 52 peaks because there are 52 weeks on a year. So this is saying that this oscillation pattern is because of daily traffic variation. And if we look at the lower figure, which is the average trips per day, we can see that on Monday, for example, we have 20,000 trips on average, whereas on a Saturday, we have almost 40,000 trips. So we see that there is a big difference on the trips on weekends versus weekdays. So we know we have a lot of daily traffic variation here. Second, we see we have some seasonal variation. If we look at the first days of the year and the last days, weeks, months of the year, we see that we have usually less trips than in the middle of the year, which is summer. So we see that depending on the time of the year, we will have more or less trips. So what we're going to do first is we want to get rid of daily traffic variation by normalizing each day by that day's yearly average. And when we do that, we see that we get rid of some of the oscillation we have on the data. We also see that we move from a number of trips, which is going to, in this case, range from 0 to almost 100,000 to a normalized number of trips, which in this case oscillate from 0 to 4, and 1 would be the yearly average number of trips. So we're going to do this for every variable, and this is how we're going to normalize our traffic data to get rid only of daily traffic variation. We haven't addressed yet seasonal variation, but we're going to do it on a later step. After we have normalized by the days, we're going to obtain the start and the end of the impact of flood traffic. To determine the start of the impacts, we're going to use the precipitation. We wanted to see if using precipitation records, we could record the start of the event. So what we said is that we're going to say that the event starts when we have more than 1 inch of precipitation. And here we have a figure which is made with real data, and we see that after we have 1 inch of precipitation, there is a drop in the number of trips. This is the normalized number of trips, which means that after the rain starts, we are losing trips. So that is the start. There we see that we are having impacts on traffic. About the end of the impacts of flooding on traffic, this is more complicated because the event will not necessarily finish when the normalized number of trips is 1, because after an event we could have less number of trips or more number of trips. So what we decided to do is to use the usual variation of the data before the event. So we can see that before the event we are usually oscillating around 1, but with the event starts we have a big drop. These big drops make the standard deviation of the data to rise. So what we're going to say is that the event finishes when the standard deviation is no longer an outlier, which will be calculated as the percentile 75 of the data plus 1.5 times the IQR, the interquartile range. So basically now we define when the effect starts and when they finish. Then number 4, functionality curve calculation. Now that we know when the effects are starting, we're going to address seasonal variation. So what we're going to do is we're going to normalize all of our data using the median value of the last 3 weeks. This is something that has been done in other studies. That's why we are choosing this method to address seasonal variation. And what this will do is that it will center the data before the event around 1. So we have a functionality of 100% before the event. And here we have a real example. We see that the curve in blue is before doing this normalization, and we see that our values are always below 1. This means that we are probably on a time of the year where we have less traffic than usual. But when we normalize, we see that the move is moving upwards, and now we are centered around 1. So we can say that these are functionality curves where we are centered around 1 before the event, and then we have a drop in functionality. So after step number 1 to 5, we have addressed all of the noise. We have addressed some daily noise. We have addressed seasonal variation. We have defined the start and the end of the event, so we can get functionality curves. So now to evaluate objective number 1 and 3, what we will do is that we're going to repeat all of these steps for all of our 5 events, for all of the traffic variables, and we're going to see how the duration of the event is working, and we're going to check all of the functionality curves that are being generated to see which one are the best. So let's go first with objective number 1, which was to set a methodology to give a start of the disruption and to determine the end of the disruption. If we look here at, here we have the 5 events. This is going to be the variable of the number of trips. And we have 3 vertical lines. On green, we have the start of the event. On light blue, we have the end of the precipitation. And on red, we have the end of the event. So let's look first at the start of the event, which is given by the green line. We see that even in all of the events, after the green line, there is a drop in functionality, which is exactly what we are looking for, because once it starts raining, we have a drop in functionality. We are having less traffic being impacted. And we would like to see it. So that works really well. So we say that the start of the event is working using the precipitation. If we look at the red line, which is the end of the event, we see that for event number 1 and event number 2, the impacts are ending really close to a functionality of 1, which is what we're looking for. And it's ending just when we hit 1. Same is going for event number 2. So for event number 1 and event number 2, we are actually capturing the end of the impacts on traffic. However, if we look at event number 3, 4, and 5, it is not working that well. I'm going to take event number 5 as an example. we see that after day 0, there is a drop in functionality, which is recovered almost in day number 3 or 4. We see that the number of trips stabilizes around 1, and our method is saying that this event is finishing almost in day number 9, whereas I think it should have ended on day number 4. Therefore, we can say that our method for determining the end of the event is not working very well, and probably we should explore other options, because for some cases, such as event number 3, 4, and 5, the events are longer than they should be. So that objective number 3, which is what are the best variables to measure traffic disruption due to flood events, we're gonna look at the functionality curves of every traffic variable. Here I'm showing 3 traffic variables, which are the number of trips, VMT, and VHT. So each figure has 5 lines, where each line is a different event. We are analyzing 5 events, therefore each figure has 5 lines. What we see here is that after day 0, for these 3 variables, but I will take number 3, for example, after day 0, we have a drop in functionality for all 5 events, which is recovered over time, and we're usually going back to a functionality of 1. We see that this is happening for these 3 variables. So in these 3 variables, we see a very similar behavior for all events, a drop which is recovered over time. We see that VMT and VHT have more noise than number of trips. However, we see the same behavior in these 3 variables. Therefore, this result suggests that these 3 variables might be appropriate for measuring disruption. And therefore, in a later stage, we can measure resilience using these 3 variables. On the other side, when we analyze the other 3 variables, which are trip length, trip time, trip length, and trip speed, we see something completely different. For example, for trip time, we see that there's almost no loss of functionality during the events. Even though we lost a lot of trips, the trips are on average, trips are taking the same time. For trip length and trip speed, we see something similar. We could say that for the event in red and the event in orange, there is some loss of functionality, but we don't see a clear trend here. Therefore, this is suggesting that these 3 variables might not be appropriate for measuring traffic disruption during a flood event. So, therefore, the conclusions of this exploratory analysis, which only consider 5 events, reasons to extract are the following. For objective number 1, which was to present a method for the start and the end of the event, we see that the start of the event looks really good. Using precipitation records to determine the start of the event looks like something we should be doing. However, the event seems too long in some events, therefore we should explore other options for determining the end of the flood, of the impacts of flood and traffic. Objective number 2, we develop a method that eliminates daily variation, most of the daily variation and seasonal variation, and it looks to be working really well. Finally, objective number 3, the results suggest that number of trips, VMT, VHT could be appropriate for measured traffic disruption, and therefore on a later stage measuring resiliency. However, average travel speed, average travel length, and average travel time might not be appropriate for measuring disruption because their behavior is inconsistent. There seems to be no drop of functionality during this event. And for future work, what we're going to do, first explore other options to get the end of the event. Then we're going to expand this research to 100 census tracts because that's the quota we have. We can expand this up to 100 census tracts. Once we do that, we're going to calculate resilience metrics for all of the events we find for these 100 census tracts. And when we have those results, we can explore the relationships between flood resilience and social demographics and see how they are correlated. And hopefully this will help in the future to see how should we allocate resources to improve the resilience of communities. In this case, would be census tracts. So that was my presentation. Thank you for listening.
Thank you, Francisco. So let's take just a few quick questions from the audience.
I have a question. I think that very interesting work, first of all. So I did miss the beginning of your talk, but one of the issues that I see in terms of estimating when the impact of the event ends is that you might end up in some sort of different steady state. And so this adds to the problem. And so I'm sorry, again, I apologize. I'm not sure if you discussed this upfront, or how to account for those situations, I think is kind of the question that I have.
Yeah. Hi, thanks for your question. So what I meant, I don't know if you saw step number 3. So as you said, after an event, we could finish with a functionality over 1 or below 1. That could happen. So that's why initially we thought about saying that the event is going to end when we are close to 1, but we're not doing that because that might not happen. We might end with a lower value or a higher value. That's why we had the idea of using the standard deviation of the data to determine the end of the event. However, it looks like this doesn't work very well because there seems to be sometimes a lot of noise on the data before the event or after the event. So it seems that it might not work. So we're gonna look at different ways to
And you looked
set
at
the end of the event.
You looked at the series, basically you looked at VMT, number of trips, you looked at these series independently?
Yeah, we are looking at all of these independently.
I see, because that's,
oh,
I'm sorry. I mean, that's kind of the idea that came to mind, which is tied to what you just said. And so the idea is that one might model functionality as a latent variable, and then to model essentially each one of these series as manifestations of that latent variable. And so you would have this underlying time series, which would be more stable, probably feed from each of these things. And I think that you can, and that was tied to my question, which is that you can do some statistical analysis about like kind of the stability of the time series and so on and so forth. And so this provides essentially like a collection of looking at the standard deviation and the mean and all of these things. I think that you'd be looking for something that collects all of these things that you are looking at independently. Also you would be able to discard statistically, like the fact that some of the other measures that you presented, that they were not related. And so the only reason why I bring it up is because I think that the visualizations that you provided, they're very compelling, okay? But I think that it could be that if you're looking at a different census tract, that things look different. Which, I mean, you were cautious in presenting your results, but I think that what might be nice is to have this integrated framework.
Yeah, so now we're thinking on more ways to get the end of the event. As you say, we could use statistical approach. We're looking right now, we are looking into time series analysis and how anomalies are being detected on that domain. So I think that we're going to look at that and we're going to see how it works. That's going to be the next step. That was one option. Yeah, that's the option we're looking for. And if that doesn't work, we're going to look maybe at other options. We don't know yet. That's work in progress right now.
Okay, let's take one more question. I have a question. So, based on what you have presented, and you basically based on the traffic data and kind of like know when the event starts and when the event ends. And I was wondering, is it possible for us to instead have some like events, and we know there's a flood event, will you like have an estimation about how the traffic volume will change, like based on that kind of event?
So what you're asking is if eventually in the future, once we have all of the results, make this work, we would be able to predict what the effects, like how much traffic we're going to lose. So in theory, we could do that.
Will it be like a possible?
Yeah, I think it could be possible because since we have the precipitation records, since we know how much rain is falling, if we had more data, we could see for a given census tract, if we have, for example, 20 inches of precipitation, we are losing X amount of number of trips, for example. That's something we could do in the future once we have the results for the resilience metrics for different events for all of the census tract. That's something we're going to do definitely. Actually, in the database we're building right now, we are recording variables such as cumulative precipitation or max daily precipitation to see how it correlates to the loss of traffic. So that's something we want to explore.
Thank you. That's really cool.
Yeah,
okay,
and to add on that, just a really extra say, and our idea in the future is that after we do that, we're going to see which are the census tracts that are more susceptible to flooding. If a census tract gets flooded with very little precipitation, that's a census tract that needs work, and maybe we should allocate more resources to address that issue.
Yeah. Thank you. That was very cool. So thank you both Adrian and Francisco, and thank you everyone for coming.
Thank you. Thank you very much. Thank you, Jing.
Yeah, thanks to you.
Thank you.